So this video is going to help you understand and see how to do the traveling salesperson problem for this lesson. On the board we have a 4-city problem with the distances between the different cities. And our goal with the traveling salesperson problem is going to be to go through and start at a start point, travel all the way through all the different cities, and come back to where we began in as quick of a way possible. There's 2 methods we're going to learn. One that's going to guarantee you get the right answer, and one that's going to be quick enough to kind of just like approximate it, and sometimes you get the best answer, but sometimes you don't. So you got to pick and choose when you use each one. This is a major math problem still, in the sense that there are a lot of mathematicians trying to find one very best way to do this for all of it. The problem is the more cities you get, the more complicated the problem gets. So we're going to use this diagram, and I'm going to show you the first method, which is called the brute force method, and then we'll jump into our shortcut idea. So the brute force method, if you look on page 242, the notes are there if you need it as well. But the idea is we're going to start in St. Louis. So think like our home base is St. Louis. We're going to start there, travel to every other city, and then come back to where we began. It's almost like if y'all were to leave from home, go to a school, go to work, go shopping, go to a restaurant, and then come back home. How would you find the quickest way to do that so you're minimizing the amount of travel, which means minimizing the amount of gas and everything? So the way we do this is really simple. We start with the tree diagram. We're going to come in here and start with St. Louis. So you create this tree with St. Louis at the top. So we'll put a point here and just list St. Louis. And then your next step says, okay, great. From St. Louis, you have 3 options. You can go to Minneapolis, Chicago, or New Orleans. So we're going to branch off 3 different ways and show those 3 different distances. So we create 3 branches out, one that's going to come over here to Minneapolis, one that's going to come down to Chicago, and one that's going to branch over here and go to New Orleans. Once you get those 3 branches out there, you want to label the distances for each branch. So the distance from St. Louis to Minneapolis is 550. The distance from St. Louis to Chicago is 270. And the distance from St. Louis to New Orleans is 910. So those are your first 3 choices. So the idea is you're going to start in St. Louis and pick one of those to go to. Thank you. St. Louis, New Orleans is not 910. St. Louis, New Orleans is 670. Okay. So now what we get is we have picked our first branch. Now we're going to look at our second branch here. And so, okay, once I go from St. Louis to Minneapolis, I only have 2 choices. I can either go to Chicago or to New Orleans. So go ahead and branch those 2 off. And we list Chicago, and we list New Orleans. The distance from Minneapolis to Chicago is going to be 400. And the distance from Minneapolis to New Orleans, the long trip, of 1260. From Chicago, we have 2 options. We can go to either Minneapolis or New Orleans. Chicago to Minneapolis is 400. And Chicago to New Orleans is 910. To go to New Orleans first, we have 2 options. We can go to either Minneapolis or Chicago. So we come down here and go to Minneapolis or Chicago. So New Orleans to Minneapolis is that long trip of 1260. And then New Orleans to Chicago is 910. So now we visited 2 of our cities on our trip. We've got to hit our 3rd city now before we get back home. So if we start with St. Louis, Minneapolis, Chicago, the only place left to go is to New Orleans. And if we go to St. Louis, Minneapolis, New Orleans, the only place left to go is Chicago. One of the neat things that happens is at this level, you're always going to be traveling between the same 2 cities. So Chicago to New Orleans and New Orleans to Chicago have the same 2 distances. So we find Chicago to New Orleans of 910. And both of those distances are 910. Now we go St. Louis, Chicago, Minneapolis, and then we can go from Minneapolis to New Orleans. Or we can go New Orleans to Minneapolis. Both those distances are 1260. And then on the last one, if we go St. Louis, New Orleans, Minneapolis, we can go to either Chicago, or we can go to St. Louis, New Orleans, Chicago, back to Minneapolis. Chicago to Minneapolis is 400. So now we visited all three cities. We traveled all possible routes here. The only thing we have to do now is go back to start. Okay? So we find each one of these, and we come down and come back to St. Louis for each one of these. And as I'm writing this up here, if you look at it, you'll see that every single one of these has a duplicate. So the first one says New Orleans to St. Louis, which is 670. And further down, there's another New Orleans to St. Louis, so we fill in 670. Chicago to St. Louis is 270. And there's a duplicate of Chicago to St. Louis, 270. And then Minneapolis to St. Louis is 550. And the same on there. So this tree diagram is showing us all the possible routes we can travel on here. And then the last step you do is you figure out the total distance by just adding everything up. Okay? So as you look through this, if we go St. Louis, Minneapolis, Chicago, New Orleans, the total distance should be 2530. With St. Louis, Minneapolis, New Orleans, Chicago being 2990. St. Louis, Chicago, Minneapolis, New Orleans is 2600. And St. Louis, Chicago, New Orleans, Minneapolis, by St. Louis is 2990. And then St. Louis, New Orleans, Minneapolis, Chicago is 2600. And the last one's going to be 2530. The nice thing about this particular method is that when you look at it, it gives you all 6 possible options on here. Only catch is you only see 3 different numbers at the bottom. The reason for that is if you start in one location and travel one direction and come back, it can take the exact same route backwards and it's the same distance. So what you're really doing on this one is you're actually duplicating the amount of work you have to do because you have to find 3 different paths going 2 different directions. So if you're looking for the shortest route on this one, the shortest route is going to be the one that totals 2530. And there's 2 possible choices. So that's going to be the absolute fastest route we can take to get from St. Louis through all 3 cities and back to St. Louis. It's a lot of work. The hard thing with this one is that you have to show all the options. It's a lot of work, really time consuming, and it gets worse the more cities you add. Just think about what happens. If I add just a 5th city on here, from the start point, I'm going to branch out instead of 3 times, I'm going to branch out 4 different times. Each one of those is going to branch out 3 times. Each of those is going to branch out 2 with another 1. And it gets that much more complicated for a 5-city problem. Now imagine somebody trying to tackle an 85,000 city problem. That is the biggest problem that anybody has actually found a solution for as of right now. Give you a hint. To find a general solution for this, you know how like in algebra class we have general equations for linear functions and stuff like that? To find a general solution that works for all possible city combinations. So 2 city, 5 city, 10 city, 1,000 city, 85,000 city, 8 million city routes. There is currently prize money out there for the mathematician that can come up with it, the tune of $1 million. So imagine being the guy who comes up with the general solution, and you just get handed a check for $1 million, say, thank you, you have helped thousands of mathematicians rest easier tonight because you found that answer. That's how big of a problem this is. So this is the brute force method, really easy to do, but this takes a lot of time. The next method is even simpler and a lot faster in the sense that it is going to do what you do naturally. So if you were to actually think about what you would do to go from your house to each individual place you visit and come back where you're going back to your home at night, your general thought is you're going to go to either the place that is closest to you, and then the place that's closest to that, and the place that's closest to that, all the way out as far as you can, and then come back that long distance back home. That's how you normally drive. If I've got to go to a store and the store is 5 minutes away, I'm going to go to that store first. I'm going to go to the store that's closest to that one, and the store that's closest to that one, and keep jumping. Or you say, well, I've got to go all the way to Greensboro, so I might as well drive to Greensboro first, and then catch all the stores on my way back in. Most of us don't like to travel in the sense that we go from, say, our home in Medon to Greensboro for a store, back to Raleigh for a store, back to Alamance for a store, then all the way up to the East Coast. We don't jump back and forth in our stops because we get the concept that it takes too long. That's the idea behind your nearest neighbor algorithm. Okay? When you think nearest neighbor, your general thought is, I want to go to the one that's closest first. And that's all we do. So we come in here and say, okay, great, from St. Louis, I've got 3 options. I can go to Minneapolis, Chicago, New Orleans. If I go to St. Louis to Minneapolis, it's going to be 550. If I go to St. Louis to Chicago, it's 270. St. Louis to New Orleans, it's 670. So we're going to pick the shortest distance first. So we travel from St. Louis to Chicago. Now I've got only 2 options. I can either go from Chicago to Minneapolis or Chicago to New Orleans. So we look at those distances, and I pick the shortest one. Chicago to Minneapolis is only 400, so we go that way. Now, I can't go straight back home yet because I need to fix and go to all my stops. So I'm forced to take that long trip back over here to New Orleans. And then once I go to New Orleans, we can go back home to St. Louis. That should have been a little bit quicker to do, would you all agree? So now the next step we do is we come in here and say, okay, great. Now you take these distances, 270 plus 400 plus 1260 plus 670, and add all that up. So 14 plus 6 is 20, 2, 2, 4, 8, 10, 16, here's 1. Total distance 2,600. Done. Is that a little bit quicker than the previous one? So here's the catch. What you're dealing with is that concept says, okay, great. This method is faster, but doesn't give us our optimal solution. Our optimal solution on the previous section that we forced into finding was 2530. Nearest neighbor algorithm gives us a total of 2,600, which is not the best solution, but was it a lot faster? And if it's a lot faster, is it close enough for us to approximate and say, you know what? If I can get pretty close to 2530, but not dead on 2530, but I can speed up my process by 10, 20-fold, I'm going to go ahead and do that option. And that's what we do naturally. This is an example of a heuristic model. It's in your textbook if you look it up for a definition, but the idea of a heuristic model, it's a model that is quick and reasonably accurate. Does that guarantee it's going to be perfect? Definitely not. So now your idea says, okay, great. If I want to be perfect, if I want the absolute fastest route, I do brute force. But if I want to be quick about it and get pretty close, but not always dead on, I'm going to do nearest neighbor. So that's the basic idea behind this. Not going to ask you either one of those two types of questions. So I hope this has helped some, and we'll see how everything works for us.